All right, welcome everybody. Today we're going to talk about lesson number 54, which is the beginning of chapter 5, and this is section 5.1, which is about using the fundamental trig identities. Now, if you're going to be using the fundamental trig identities, you of course have to know what those trig identities are. So let me go ahead and pop over for a second to the chapter 5 formula sheet. This is something that you are going to want to print out or save a copy to your computer. You're going to want to have this for easy access, really for the entirety of chapter 5. Even in a regular school year, you would not be required to memorize any of these formulas. The ones that we use the most frequently, you'll probably start being able to use without looking them up. But obviously you can see there's a front, there's a back. So there's a whole bunch of formulas that we have to be familiar with. This in your class notebook, I left a blank page at the top, a blank copy, so you can refer to it. And then here I'm going to mark up the one at the bottom in case you want access to that. So taking a look at these formulas, we're only going to go ahead and talk about the first set for today. And the first thing that I want to point out here is that these are going to work for any variable. So if you notice, a lot of them are X's and then some of them are U's. Part of it has to do with the version that your book uses, and then there are some reasons behind the other ones, but please know that they work for any variable. When it comes to the homework problems or the note problems, some people prefer to make everything an X for now, so it is perfectly fine if you do that, but please make sure that you're aware that it does work for any variable. Of these different sets of identities, you probably are the most familiar with the reciprocal ones. You already know that cosecant and sine are a pair of reciprocals, similarly for cosine and secant, and then also for tangent and cotangent. So the six identities that are listed under the reciprocal are really relationships that you already know. And then similarly for the quotient identities, while you might not be as familiar with these, remember, of course, that a tangent is a y over an x, and a cotangent is an x over a y. So if you're thinking about your unit circle, the fact that sines are y's and cosines are x's, it should hopefully make sense to make the jump of why the tangent equals sine over cos and the cotangent equals cosine over sine. Then when it comes to the even and odd identities, so you can think of these in terms of their graphs. If you were to go back to the last section and you were to look at their graphs, you had to decide if they were even or odd based on a couple of different things. So as a reminder, remember that if you're talking about a graph being odd, you're talking about origin symmetry. And algebraically, you're talking about getting the opposite. So your odd equations here are going to be the ones where you're getting the opposite. So here's an example of an odd and an odd and an odd and an odd, basically any case where you're getting the opposite. So then hopefully you remember what it means to be even. Even means that you are going to have y-axis symmetry, and algebraically, it means that you wind up being the same. So that would mean that the cosine would have to be an even function, and similarly for the secant. So not only should you be able to identify which functions are odd or even, but you also have to understand the formula. If you were asked to find the sine of negative u, you could replace it with the negative sine of u. And again, as we get into the problems, you'll see why that will or will not be helpful. The next set is the idea of the set of co-functions. So when you see the word co-function, focus on the co and think of the word complements. Hopefully you remember that a complement means adds up to 90, and that's what these formulas are showing. We've kind of seen these relationships unofficially, but now they're just kind of stating them outright. The sine of pi minus u is equal to the cosine of u. So again, I want to just point out, whatever the value is inside the parentheses, pi over 2 minus u and u, those are a pair of complements, meaning they have to add to 90. Same thing for this pi over 2 minus u and u, they have to be complements, which means they have to add up to 90. Hopefully you can understand why, if you were given the left side, it would be a little bit cleaner to go ahead and be able to write it at the right side. So we're going to be doing a lot of simplifying. So again, going from the left side of the equation to the right side certainly is going to make things a little bit easier. When it comes to the co-functions, everybody has a partner, and those partners do not change. So important to point those out. So the sine is always going to be partners with the cosine. Similarly, whether you have the sine or the cosine on the left or the right, those are always going to be partners. When it comes to the tangent, he is always going to be co-function partners with the cotangent. And then when it comes to secant, he is always going to be a co-function partner with the cosecant. So again, you don't have to memorize anything. You only have to be able to use this sheet as a reference. So make sure that you're either marking up your own copy or that you know where to find this copy in class notebook. So you'll notice I skipped the ones at the top, but those are actually the most important and perhaps the one that you're going to wind up using the most. Those are called the Pythagorean identities. So to give you a little idea of where the Pythagorean identities come from, you have to think about the unit circle for a second. If you think about the unit circle for a second, remember the equation for a circle is x squared plus y squared equals 1. Then remember that on the unit circle, cosines are x's. And remember that sines are y's. So if you were to square a cosine, you would get a cosine squared. If you were to square a sine, you would get a sine squared. So that's how you're able to find our first identity here, which is sine squared plus cosine squared is equal to 1. Again, it comes from the unit circle equation for a circle, replacing the x with a cosine, the y with a sine, and then just simply inverting the order. So sine squared plus cosine squared equals 1. Something important to point out here, notice where the squareds are. The squareds are between the function and the variable. That is where they always have to be whenever you're talking about a squared. So please make sure that you are putting them in the right spot. So then if you take sine squared plus cosine squared equal to 1, if you were to take that equation and if you were to divide everything by sine squared, that would lead you to the second Pythagorean identity. So sine squared divided by itself would be 1. A cosine divided by a sine is a cotangent. So a cosine squared divided by a sine squared is a cotangent squared. And then 1 over a sine is a cosecant. So 1 over a sine squared is a cosecant squared. So that's going to go ahead and lead us to our second Pythagorean identity. Then if you were to go back to the sine squared plus cosine squared equals 1, and if you were to instead divide each of those original by cosine squared, that would actually lead you to the third example. So if you were to divide everything by cosine squared, sine squared divided by cosine squared would be tangent squared. Cosine squared divided by itself would be 1, and then 1 divided by cosine is a secant, so 1 divided by a cosine squared is a secant squared. So again, this is just the background, making sure you understand where each of these equations come from. It's not necessarily like I would ask you to explain it in a future assessment, but it still is really, really important to know. So a few other things that I want to point out here, some rules for how you can use the identities versus how you can't. So when it comes to the reciprocal and the quotient, I want you to realize that these can work for any power. And I kind of illustrated that a couple minutes ago. So what that means is that if you were talking about a cosecant squared, you could write that as 1 over a sine squared. Or if you were talking about a tangent squared, you could write that as a sine squared over a cosine squared. So when it comes to the reciprocals and the quotients, you can write them as any power. That is absolutely not the case when it comes to the Pythagorean identities. So when it comes to the Pythagorean identities, they must be squared only. I can't emphasize enough how important it is that they be to a power of 2 only. Redraw that in so you can get it later. It only works for squared. It doesn't work for any other circumstance. So you have to be really careful not to make up a fake identity. The second thing that I want to point out about the Pythagorean identities is that you can rearrange these. So what I mean by that is look over here at tangent squared plus 1 is equal to secant squared. If this identity is true, it means it's also true if I take tan squared and I rewrite it as secant squared minus 1. So you are allowed to rearrange those Pythagorean identities as long as you do it carefully, keeping in mind that when you move things from one side of the equals to the other, they are, of course, going to change their sign. So lots of important background information here in terms of where these equations come from. Again, there's a clean copy up at the top of the page, and you're definitely going to want to print out your own copy, I would assume. What is it that we're going to do with these identities? Well, so now we're going to take a look at lesson 54. And I just want to point out that this is the same worksheet that you have. I simply made it a little bit larger so that I'd have a little bit more room. So if you take a look at problem number 1, the directions are to simplify, whereas in number 2, the directions are to factor. So the directions for number 2 are giving you a little bit more of a suggestion of how to approach it, where when it comes to simplify, you kind of have to figure out what it is that needs to be done. So over here for number 1, when it comes to simplify, turns out that we actually do also want to factor it. What is it that we want to factor? Well, we want to factor out the greatest common factor. You factor by using the terms, and remember that terms are separated by pluses and minuses. So I've highlighted the 2 different terms. If you're looking for the greatest common factor, hopefully you would agree that the greatest common factor would be a sign. So I'm going to go ahead and factor out a sign. If you factor out a sign from sine times cosine squared, you're going to be left with a cosine squared. And remember, make sure that you put your squared between the cosine and the variable. If you take a sine away from a sine, you've taken out the whole thing and you're left with a -1. Hopefully, when you see that 1 and hopefully when you see that squared, that reminds you of one of the identities. So until you get to the point where you kind of can rewrite it automatically, if you take a look at your formula sheet here, you're going to take a look at the squared identities, and you're looking for cosine squared -1. Now, cosine squared -1, let me just go back to the clean copy here, make it a little bit easier. So cosine squared -1 is currently not one of the identities, but you can make it one of the identities. If you go ahead and take cosine squared and subtract the 1, that is going to be equal to negative sine squared, which means you're allowed to go ahead and make that replacement. So here in my notes, I'm going to go ahead and replace this cosine squared -1 with negative sine squared. That's still going to be multiplied by the original sign. And if you're multiplying a sine times a sine squared, you're going to get a sine to the third, and it's going to be negative. So this entire expression that you started with is in fact equal to negative sine cubed of x, and that's as far as you can go for now. Again, why are we doing that? What's the point? That becomes clearer the more we get into chapter 5. For now, you're simply practicing the mechanics and the skills, and then also becoming more and more familiar with the identities themselves. Take a look over here at number 2. The directions are to factor. So secant squared -1, there obviously is no greatest common factor. What I'm hoping that you realize, or even if you don't realize, you understand after I point it out, is that this is really the difference of squares. If I was to ask you to factor x squared -1, you would hopefully easily be able to do so as x plus 1, x minus 1. So you're going to go ahead and factor this in a similar way. You're going to have 2 sets of parentheses. One of them is going to be a positive and one of them is going to be a negative. You would put the square root of the back in the back, so 1 and 1. You'd put the square root of the front in the front, which would be a secant and a secant. And turns out that is as far as you can go for this problem here. You're going to factor that as the secant of x plus 1 and the secant of x minus 1. Again, there are eventually many more steps that will happen. For now, you're just trying to practice the mechanics. Other factoring strategies that you know and love from the olden days, you're allowed to go ahead and apply those to trig functions. So taking a look at number 3, 4 tangent squared plus the tangent minus 3. The first thing you notice is that everybody is a tangent, and that's good because obviously it's easier to factor when that's the case. Then hopefully you realize that there's a 4 out front, which means it's a little bit trickier whenever there's a coefficient. And then hopefully the last thing you realize is that this is actually very similar to 4x squared plus x minus 3. So again, this is the idea of being quadratic form, meaning that you're going to factor this tangent expression the same way you would factor a regular quadratic expression, also known as U substitution. Some of you might be able to just factor with no work, but if you do need to show some work, this would be the AC method. So if you're going to do the AC method, you're going to go ahead and multiply the A times the C, which would be 4 times -3, which would be -12. You would then be looking for two numbers that multiply to be negative 12 and add up to be positive 1. Hopefully that you can see that that would be 4 and negative 3. When you go to rewrite the middle term here, though, don't forget the tangent. So 4 tangent squared, and then the 4 becomes a 4 tan x minus 3 tan x minus 3. Now you're going to use your grouping. So you're going to group the first two, you're going to group the second two, and you're going to take the GCF out of both. So the GCF of the first pair would be 4 tan of x, and that would leave you with a tan x plus 1. For the next two, when in doubt, take the negative out, which would be a negative 3, which would also leave you with a tan of x plus 1. Remember, that's the dream, because whatever you get for that repeat, that's how you know you're doing it right, and that's going to be half your answer. And then whatever it is you factored out is going to be the second half of your answer. So now you have officially factored the problem down to two different binomials. Again, it's possible that you would have been able to factor it without actually showing that AC work. And if that's the case, then more power to you. But for now, it is important that you're able to remember the factoring skill, whatever means you have to do so to get the answer. Let's take a look then at number 4. The directions still say factor, but a little bit of a twist. Notice here that you have a cosecant squared and you have a cotangent, and you have a cotangent. So obviously those variables do not mix, or those trig functions do not mix. They're not the same. So it would obviously be much easier if they were the same. So whenever you find yourself in a situation where you have too many different functions, that's a clue to you that you're going to want to make some kind of a replacement with the identities. So if I go back to my formula sheet here, because of the fact that there's a squared, that's kind of a clue to you that you might want to look at that first set. So looking at the previous problem, if you look at what was squared, you had a cosecant squared. Luckily for us, a cosecant squared is equal to a 1 plus cotangent squared. So you're going to go back and you're going to just make that replacement. So I'm going to replace this cosecant squared with a 1 plus cotangent squared minus cotangent minus 3. That's very good news because it's now a cotangent party, and I'm just going to go ahead and rewrite it whilst combining like terms. So cotangent squared to start minus the cotangent minus 2. You are also going to factor this just like a quadratic, but the fact that there's only a 1 out front means that you can do it hopefully without the AC method. Instead of factoring it x and x, you're going to factor it as cotangent and cotangent. Factors of negative 2 that add up to be negative 1 would be negative 2 and positive 1, and that's going to go ahead and be your final answer. Now, it's not equal to anything yet. It will be eventually, but again, for now, you're just going to go ahead and leave it as such. All right, so here in number 5, again, we're back to a direction of just simplify. So again, unfortunately, the simplify tells us the least about how we should go ahead and get started. And if nothing else, the first 4 problems, even if you didn't really like factoring, at least it was something obvious and something familiar. Some of the operations that I do in these last couple of problems might not seem obvious to you yet because you're just doing them for the first time, but give it a couple days and there'll just be a couple of tools in your toolbox that you'll start automatically thinking about. So here for number 5, we have a sine, we have a cosine, and we have a cotangent. Because of the fact that you have a single sine to the first power and a single cosine to the first power, means you're not going to be able to use those Pythagorean identities. So instead, I'm going to go ahead and focus on the cotangent. That cotangent, if I go back to my formula sheet, a cotangent is equal to a cosine over sine. And while maybe you're not sure why that's helpful off the bat, let's go ahead and give it a shot. So I'm going to go back and I'm going to rewrite that cotangent as a cosine over a sine. So this is now going to become the sine of x plus the cosine of x over the sine of x. And then that's being multiplied times the cosine of x. The one thing that I can see is that now at least it's all sines and cosines. So that's a good thing. This is the cosine over the sine, technically being multiplied by the cosine over 1. So I'm going to go ahead and actually multiply them. If I'm going to go ahead and actually multiply them, I'm going to multiply the top times the top and the bottom times the bottom. So a cosine times a cosine gives me a cosine squared, and then a 1 times the sine gives me a sine. Again, maybe it doesn't seem obvious what the next step should be, but the next step should be, I want to go ahead and I want to actually add those terms, which I'm going to do with a common denominator. So this is sine over 1 plus cosine squared over sine. The common denominator of 1 and sine would be sine. In order to turn this sine over 1 into something over sine, I have to multiply top and bottom by sine over sine, and that's going to give me a sine squared. And then I still have my cosine squared. Again, from here, once you have these squared values, sine squared plus cosine squared, hopefully you think to yourself, I think that's a Pythagorean identity. Sine squared plus cosine squared, look at that, is simply equal to 1. So you're going to go ahead and make that replacement. This is 1 over sine. And then if you go back and look at your formula sheet, 1 over sine is simply equal to a cosecant, which is what we're looking for. So perhaps you can see value of taking this somewhat messy and long expression and turning it into a nice simple cosecant. And if you can't see the value, well, you should. But again, when it says simplify, those are kind of, again, just sometimes the hardest to figure out how to get started. But the whole point of this lesson is to give you some tips of how you would get started. So take a look over here at number 6, perform the addition and simplify. So the fact that they're telling you to perform the addition, that's helpful because they're telling you literally to add these two things. The way that you're going to add these two fractions is the same way you did in the previous problem. You're going to find a common denominator. Now, a little bit more difficult because these denominators are a little bit more difficult. So 1 plus sign and 1 minus sign. The first thing I need you to realize is that those are each binomials. So you might want to put them inside of parentheses. You are not allowed to break those up. If I was going to ask you to add a half plus a third, if I asked you for the common denominator of 2 and 3, you would hopefully say 6. Why? Because it's these two things multiplied times each other. So it's the same idea here. The common denominator of 1 plus sign and 1 minus sign is simply those two things being multiplied times each other. So that's going to be my common denominator. Then for the numerator, I would have to multiply this fraction by 1 minus sign over 1 minus sign. So in the top, 1 minus sign. Then this is an addition sign, so addition. I would have to multiply this term by 1 plus sign over 1 plus sign. So that's going to give me 1 plus sign. Taking a look at the numerator, some good things happen. The good thing is the fact that you can cancel out those signs. So negative sign plus positive sign cancels out. 1 plus 1 makes it 2. And then here's where you have to start being able to realize, should you multiply the denominator out, yes or no? The general rule is that if they are a pair of conjugates, remember conjugates means same front, same back, and opposite middle, then yes, you should multiply them. Because if you do, instead of doing the whole FOIL, you only need first and last. So 1 times 1 is 1. Last would be negative sign times positive sign, which would be negative sign squared. Again, that 1 and that squared is a clue to you that you're going to go back to your formula sheet. You're going to take a look at the identity that has those two things. So that's going to be sine squared plus cosine squared equals 1. If you go ahead and rearrange that so that it is equal to 1 minus sine squared, that is going to be equal to a cosine squared. So you're going to go ahead and go back and make that replacement. So this is going to give you 2 over a cosine squared. And then again, hopefully you can go back and take a look at the fact that this is equal, or just algebraically, this would be equal to 2 times 1 over cosine squared. And then because 1 over cosine is a secant, 1 over cosine squared is a secant squared. So this entire expression, that big, ugly fractional addition, turns out to be just a simple 2 secant squared. So even if you wouldn't have thought to yourself of finding a common denominator or using those conjugates, again, that's the point of today. A little bit of a longer lesson, always to start us off, something to give us some clues how to go forward. So let's take a look at number 7. Again, perform the addition. So hopefully by this point, okay, perform the addition means I'm going to add these guys. And if I'm going to add these guys, I'm going to do so with a common denominator. So the common denominator of the denominators is just those two things multiplied times each other. So that would be the sine times 1 plus cosine. You would have to multiply the left fraction times sine over sine. So that's going to turn this sine into a sine squared. And then again, it's an addition. You would have to multiply the right side by 1 plus cos over 1 plus cos. So that means you're going to have a cosine times a 1 plus cosine. So in the numerator, that's going to give you a sine squared plus a cosine plus a cosine squared. And again, I get that by distributing. Again, when it comes to your denominators, you're always going to ask yourself, should I multiply them or not? Generally speaking, if it is a pair of conjugates, yes. If it is not, no. So sine times 1 plus cosine is not obvious to me if multiplying them is going to be helpful, so I'm not going to. So then there's a little bit of a hidden identity there in the top. You have a sine squared and you have a cosine squared. Even though they are not next to each other, they still together make a 1. So I'm going to replace all that blue with a 1 plus cosine over my still unmultiplied denominator. And then if you realize that the numerator is a 1 plus cos, and then in the denominator, you have a sine times a 1 plus cos, you can actually reduce those 1 plus cosines. That's going to leave you with a 1 over sine. And whether you have to go back and check in your formula sheet or not, that is equal to a cosecant. I mean, who doesn't want to live in a world where that big, ugly, messy problem turns out to be a nice, simple cosecant? Oh, beautiful thing. I'm actually going to jump to number 9 for a second before we go back to number 8. So take a look at number 9. Rewrite that expression so that it is not in fractional form. So rewrite means do something, and not in fractional form means I don't want to have a fraction in my answer. So that can actually mean a couple of different things. This strategy might not be obvious to you, so I'm going to give you a hand. Taking a look at the denominator, the fact that the denominator is 1 minus sine, again, because there's no squared, there really isn't anything to be done. Because I have a 1 and because I have a sine, though, if I look at the numerator, cosine squared, is there a way to take that cosine squared and somehow get some sines or even some 1s? Well, there is. If you go back to your formula sheet and you just want to isolate the cosine squared, we've already done that from the previous problem. That's equal to 1 minus sine squared. So you're going to go ahead and rewrite the numerator as 1 minus sine squared. Now, don't get crazy. You can't cancel those 1s. You can't reduce those signs. As long as there are additions and subtractions and not multiplications, no reducing is allowed, so no cheating. What you can do, though, is hopefully realize that in the numerator, 1 minus sine squared, if you go all the way back to example number 2, you can go ahead and factor that using the difference of squares. So 1 plus the sine of x times 1 minus the sine of x, remember, same front, same back, opposite middle, and that's going to be over 1 minus sine. Now that you factored it, now please cancel by all means, which means you're going to be left with 1 plus sine. That is your final answer. And again, they said rewrite it so that it's not in fractional form, and you've done so. So last but not least is number 8. And I left number 8 for the end because it's actually a strategy you would not think to do without my advice. So put a star or just make sure you pay extra close attention. Again, you're trying to rewrite it so that it is not in fractional form. 1 over 1 plus sine. There is really not a lot to be done here. There are no squareds. The only thing you could rewrite the sign as is a 1 over cosecant, and that does not seem like it is going to be helpful. So here's the strategy, which again, you would not think to do without me. So you want to create square terms. In order to do that, you are going to multiply top and bottom by the conjugate. We've seen conjugates a couple times today, but mostly they kind of made themselves organically. Now we're going to go ahead and force there to be a conjugate. So what does that mean? Well, that means I'm going to take 1 over 1 plus sine. I'm going to remind myself that 1 plus sine has to stay together, or should stay together. And I'm going to multiply the top and bottom by the conjugate of 1 plus sine, and the conjugate of 1 plus sine is 1 minus sine. So again, why do I want it to be 1 minus sine? Because that is the conjugate. Why do I have to do 1 on the top and 1 on the bottom? Because if you simplify, that's technically equal to 1, and multiplying by 1 is always allowed. So then, in terms of multiplying on the top, 1 times 1 minus sine is 1 minus sine. Remember, in the denominator, should I multiply these out or not? Because they are conjugates, that is usually a clue to you that you're going to want to go ahead and do so. So 1 minus sign over 1 minus sign squared, we're kind of doing the reverse of what we did in number 9. In number 9, we started with a cosine squared and rewrote it as a 1 minus sign squared so we can factor. Now we're working in the opposite direction. So 1 minus sign squared, if I go back and I take a look at my formula sheet, 1 minus sine squared is simply equal to cosine squared. So I'm going to go ahead and make that replacement. And then in the final step, you have to think back again. These are all algebra techniques. You can use the heart technique, meaning that if there are more terms on the top than the bottom, you can go ahead and break up that heart into the following. So 1 over cosine squared minus sine over cosine squared. 1 over cosine squared, that is equal to a secant squared. You can rewrite sine over cosine squared as sine over cos times 1 over cos. All you've done is separate the cosine in the denominator. And again, you would know that that's allowed as long as you can multiply it back to get to the original. So in your final answer, you're going to get a secant squared minus a sine over a cosine is a tangent, and a 1 over a cosine is a secant, and you're going to go ahead and leave it as such. So again, I would say this is the least obvious strategy, probably one you would not have even thought to think of without me. And again, the strategy is multiplying by the conjugate, and the more we do of these, the easier it's going to get. So hopefully you could realize why maybe it was a good idea to watch this for homework, because now the actual homework that goes along with it is this problem set of 54. So as you've watched this video at home, feel free to start the homework if you want, but you do not have to. The whole point of this is we're going to work on this homework tomorrow in class. So if you are starting a problem and it's not obvious to you what strategy or technique to use, I'm going to be there to help you, or you could potentially be working in a group. So we're going to try it and see how it goes. So thanks very much for tuning in, guys, and we will catch you next time.